Welcome back to 15-Minute Math. I think this is going to be our last video on techniques to evaluate limits. We still have a couple more topics involving limits, but I think as far as just kind of straight strategies, this might be our very last one. So let's just jump right into it. We're going to evaluate what's called difference quotients, or the limits of difference quotients. And I know this is frustrating for beginning calculus students because they're kind of confusing. They definitely take a little while to crunch through the algebra. And it doesn't seem real motivated, but you're just going to have to put some faith in me and trust when I say that these will become useful very shortly for us. But it's not quite clear where they're coming from right this second. And, you know, if it was me, I probably would introduce these later. But I know in a typical calculus curriculum, these get lumped in with the various strategies of limits, so that's where I'm going to put it in my playlist. And so like I said, I know it doesn't feel very motivated, but these will become important, so just kind of bear with me and let's get through this together, I suppose. And so I don't have a lot of theory for us here. We're just going to present some examples and work through some examples. And this is typically how you'll see these difference quotients presented. You're going to find that indicated limit, and then it's going to tell you what function, is defined by f of x. Here, f of x is just some quadratic function. So maybe we should go through and we should just kind of remember what this really means. How do I find f of x plus h if I'm given a function f? And so we'll come off to the side and do that. Remember, when I'm finding f of something, it just really means plug that something into my function. So maybe I'm going to color code this blue. So what I'm going to do is I'm just going to substitute x plus h into my function anytime I see an x. So notice I'm just kind of leaving some blanks where the x's were. And now I'm going to substitute x plus h. So that's how I, find f of something. And now I'm just going to work this out. Now don't forget, when I have a binomial squared, I don't just square the first term and square the second term. You have to FOIL that out. So somewhere off to the side, if you can't do that in your head, you're going to have to write out, okay, x plus h, and literally FOIL that out. Or you can use your little binomial squaring shortcut that says that when I square a binomial, you end up with the first term squared, you end up with the last term squared, but you also end up with twice the product of the two terms. So 2xh, twice the product of the two terms. But if you don't remember that, you can always just FOIL it out. And then, of course, that's going to be plus 3x plus 3h, just distributing there, and then minus 7. And now I'm going to drop the color coding because I feel like at this point we're just on cleanup duty. Oh, let's see. We only have one x squared term. Well, there's really not much we can do here. I was thinking maybe we'd have some like terms to collect, but I really don't see any like terms. So really this line is kind of redundant. Anyway, so this is my f of x plus h. So when I think about this difference quotient, this is almost like a set of instructions on what to write. First, I write f of x plus h, which I just figured that out. So let's see here. I'm going to come off to the side just a little bit. Hopefully I can get this all on one line. So first thing I'm supposed to do is write f of x plus h. And maybe I will go ahead and... do I have enough colors to color code this? We'll see. Green is going to be f of x plus h. So it's going to be x squared plus 2xh plus h squared plus 3x plus 3h minus 7. And then the second thing I'm supposed to write is just f of x. Well, f of x is right there. So I'm going to subtract, notice I'm subtracting f of x. So I'm going to make sure I put those in parentheses so I don't have any sign errors, right? Because we'll end up like distributing that negative throughout my quantity here. And then on the bottom, I just have h. So that's kind of the third piece of this puzzle. And it just kind of is what it is. It's just h. All right. So, I mean, that is what my difference quotient is. I know it seems nasty, so let's try to clean it up a little bit. I mean, one thing I can do is I can distribute that negative across the quantity kind of on the back end of the numerator there, and that's what I'm going to do. And then after I do that, we're just going to kind of see if we can have any cancellations. Hopefully we do have some cancellations. So when I distribute this negative, that's going to be minus x squared minus 3x plus 7. And of course, we're all divided by h. All right. And so let's see here. Notice that I can have, I have minus 7 plus 7. That'll cancel. Plus 3x minus 3x. That'll cancel. X squared minus x squared. That will cancel. And so let's write out what's left over. Why did I write h right there? That is not what I wanted to write. I want the limit as h goes to 0 of, I'm going to, again, drop the color coding at this point. So it's just going to be 2xh plus h squared plus 3h, all divided by h. And you might be thinking to yourself, wait, I mean, we still can't plug in 0, right? Because I'm going to have division by 0. So it's not immediately obvious that all those cancellations really helped us, but they actually did. And the reason is, if we look in the numerator, notice every single term has an h in it. So I can factor out that common factor of h, and I'm just going to be left with 2x plus h plus 3 over h. Now I can cancel. And so now I'm just left with the limit as x goes, as h goes to 0 of 2x plus h plus 3. And there's no problem with plugging in 0 for h right now because, I mean, I don't have division by 0, I don't have negatives under radical, I don't have anything that would cause me problems. So if I plug in 0 for h, I just get 2x plus 3. Which might be the first time that when we evaluate a limit, we don't get like a numerical answer, we get an algebraic expression. But that's just what it is. I mean, when we work out our limit, this is what it turns out to be. So there's no problem with getting an algebraic expression instead of just some number when we evaluate limits. So don't let that kind of throw you off. That happens, and in fact, with difference quotients, that happens quite often. It doesn't have to happen, but very frequently it does. So let's move on to our next example. And if we have time, we'll work a third example. I'm not convinced we will. So like before, let's first just kind of come off to the side and work out what f of x plus h would be. And so that means to say 5 blank plus 11, and inside of that blank goes x plus h, just like we did before. Let's distribute. Doesn't seem like there's going to be like terms. And so let's just kind of come over here and write out our difference quotient. Now remember, this is just like a set of instructions. First, we're going to write f of x plus h, which is this. So it's going to be 5x plus 5h plus 11. Then we're going to subtract. In parentheses, we're going to write out f of x. Well, this is f of x, so that's 5x plus 11. And we're going to divide through by h. And just like we did before, let's distribute that negative sign across that quantity and hope for some cancellations. 5x minus 11. So I just distribute the negative across those parentheses. Let's see here. 5x cancels negative 5x, and positive 11 cancels negative 11. And so I just get the limit as h goes towards 0 of 5, 5h over h, which those cancel each other. So that's nice. That takes away our division by 0 problem. But notice we now have kind of a weird thing. I think this freaks people out sometimes. We have the limit as h goes to 0 of 5. And this causes confusion. It's just like, well, where do I plug this 0 into? I'd like to be able to plug in 0 somewhere. But just think of this as a constant function, and it's constantly 5. And so if we think about like the limit graphically, here's my axes. Let's say 5 is here, so we just have a constant function. Well, as I approach 0, if this is a constant function, then my limit as I go towards 0 is just going to be 5, since that function is identically 5. So we just get 5. So in this case, we do get a numerical answer. So sometimes on these difference quotients, you'll get some algebraic expression. Sometimes you'll get a numerical answer. And I've got 4 minutes to try to work through this one. And I'm feeling ambitious, so let's go for it. All right, so if I find f of x plus h, I'm just going to have 5 over blank, and inside that blank is x plus h. So let's take the limit as h goes towards 0 of, well, first we write out this, so that's going to be 5 over x plus h minus, now we have f of x, so it's going to be 5 over x. Remember, this guy is f of x right here. And that's all divided by h. And if you just watched the last video on the playlist, you might now realize why I chose this example, because we have a complex fraction now. So we just learned how to solve these things. We multiply the top and the bottom of our expression by the LCM of the denominators of our complex fraction. In this case, it's x times x plus h. And so now when I distribute, let's see, our x plus h's will cancel. If I distribute here, my x plus h's cancel, so I just get 5x. And when I distribute here, my x's cancel, and so I'll get 5 times x plus h. And that's all going to be divided by h, x plus h. I'm going to do that thing like what we were doing a little bit ago, where we're not going to multiply out our denominators. We're just going to leave them as they are and hope it all works out for the best. It seems like it typically does. So as we've done before, we're going to simplify the numerator. So this is going to be minus 5x minus 5h. I just went ahead and distributed and kind of took care of the negative sign all in one step. That's going to be over h, x plus h. Notice that my 5x's cancel, so that's nice, I suppose. And so now I get the limit as h goes towards 0 of negative 5h over h, x plus h. And we get one more cancellation. This h can cancel that h. And so actually now I can plug in. So I'm just going to go ahead and plug in. So if I plug in 0 for h, notice that's no longer a problem. I'm just going to get negative 5 over x plus 0 if I plug in 0 for h, which of course is just negative 5 over x times x, which is just negative 5 over x squared. So again, we get an algebraic expression, not a numerical value, but that's okay. That is, again, just want to emphasize that it's typical of difference quotients. Don't let that alarm you. So wanted to just bring that back to our attention, the method of using the LCM to simplify a complex fraction. Just because we're doing difference quotients, that doesn't mean all our other strategies aren't in play. We can still factor and cancel. We can still rationalize numerators, denominators. We can still use LCMs just like we would with any other limit. I think probably the emphasis for these sorts of things is to kind of figure out this f of x plus h first, and then just interpret the difference quotient as kind of like a set of directions telling you what to write down. And at that point, you're just simplifying, some algebra once you understand what the difference quotient is telling you. If you keep that in mind, shouldn't be too difficult. I think we're closing in on time, so that will conclude our video.